Thank you very much for that very kind introduction. I just want to make sure I've got this here. So, I was asked to give, can we turn these off? Asked to give a talk tonight that would actually be an opportunity for you to, is this echoing? I don't want to burn anybody's ears out. An opportunity for you to see some of the exciting kinds of research that are being done at Penn and everywhere. And one, I come as an ambassador. Can you hear me? Should we just have these on? Keep going? Okay. So I come as kind of an ambassador from the field of neuroscience, and being a neurologist, all my life has been sort of wrapped up, my personal life is sort of wrapped up with my research life. I am fascinated by the brain. I've always been fascinated by the brain, and I kind of take my day job home with me. And so I've been very interested in sort of how our brains work across our lifespan, and I thought I'd tell you a little bit about that tonight. You mentioned that I'd written a book on the teenage brain. I'll cover a tiny bit of that in here, but that happened not because it was my day job. It actually happened because I realized while I was doing all this research that I actually had an experiment going on in my own home, which are my two teenage sons. So, you know, this shows how, like, it just blends, right? Life and your work. So what I thought I'd do today is give you a chance to learn some new neuroscience, and you're going to actually learn real science. I'll show you some real figures from real journal papers, and I guarantee you're going to be able to understand these. So 21st century neuroscience. We're the youngest, basically, biological science that is in the medical field at this point. It is about 15 to 20 years behind cancer research. And it's really because the brain is the most complex organ in the body, and it's really taken a really long time to understand the complexities, the wiring diagrams of the brain. I'll show you some of the experiments of how this is actually done, the molecular signals of the brain, how we learn. This is what we're going to talk about, because it's the essence of what makes us human, is that we can learn and remember things. So there's a huge amount of amazing research that has come out from remember that decade of the brain? Remember vaguely hearing about that? Well, the decade of the brain occurred, and that was a lot of basic research. But more importantly, in the last couple of decades, in the last decade actually, there's been a huge amount of new technology that has been able to be applied to the human brain, not just, you know, molecules and you know, cell culture experiments. And this is what has really revolutionized our ideas about how the brain works. And I would say, I'd just like to take a minute to say that I think Penn, possibly one of the things that attracted me to come to Penn after 30 years at Harvard was the fact that this is really a place where, for neuroscience, the fact that we have to get outside our box. We've got to be talking to the engineers. We've got to be talking about decision-making, behavioral neuroscience with our Wharton colleagues. We've got to be talking to the nanotechnology school about, like, tiny probes in our brains. All these things are possible when you're actually on the same campus. This is a very special place. And I'm doing a lot of visioning around this with the university. I was just actually meeting with Steve Fluharty, who's the dean of the School of Arts and Sciences, about this just today. And, you know, imagine that. I can be a doctor and just walk literally across to Houston Hall on the other side and go meet with him as a chair of a medical department in a hospital. It's amazing what we can do. We're interacting with engineers all the time. And so it's really the time to be at Penn. And I just want to tell you, this is how excited we are in the neuroscience community. This is the kind of place that the new discoveries are going to come out of because of the adjacencies that we have with our colleagues in so many other areas. It's neuroscience is time, and we need to get outside our box. So Penn is the place, and Penn is actually probably has the highest concentration of neuroscientists, of brain scientists, actually, I don't think this is working anymore, of brain scientists actually in one place on one campus, and that's really important for you to know. So the other important thing from the field of medicine is that brain science is actually going to be a really prevalent issue moving forward. If you look at this graph, which I think you'll be able to understand, disability adjusted life years means the burden of disease. And I bet you would have all thought, I shouldn't have shown this slide, you would have thought if I said cancer, heart disease, I bet you would have raised your hands as those were like the biggest problems in society. Well, look at this graph. Look at where the biggest burden of health care, and this was in 2010, it's actually even more now, and in the developing countries, it's even further. So this is data that we got from the WHO and NIH when I actually used this at a neurocaucus in Congress, actually, to try to jazz up, our Congress members who seem to be like immune to science knowledge. And so, this is a really, 1 in 4 people have mental illness, ranging from anxiety to full affective disorders like schizophrenia. Stroke, Alzheimer's, and epilepsy are 3 major diseases that affect the brain. And the burden is so huge because these diseases are downwardly socioeconomically mobile. They bring you down. They take your ability to be yourself in society out of you. And so we feel very compelled that we're finally getting to the point in science now to actually address a lot of diseases in neuroscience. And we have interventions now. We can reverse some strokes at 24 hours out. We can do laser surgery for epilepsy. We can actually have new infusions that are all but almost curing multiple sclerosis. We can take clots out. We can use immunotherapy on brain tumors. It's like a different world. It's changed so much from when I started medical school in 1983. It's just changed so much. So your brain, let me tell you a little bit about your brain. So your brain has about 100 billion brain cells, neurons. It has about 100, these neurons have to talk to each other, and they talk to each other by sending pathways across the brain, back and forth, from side to side, et cetera. And they connect to each other through something called a synapse. So they're talking to each other. They have electrical signals that they send across a synapse, and I'll show you that in a minute. And you have 100 trillion of these synapses. And you literally have miles of the roadways between these neurons that are packed into your brain. So it's growing really fast, as you can see. It starts off at 350 grams when you're born, and it becomes 3/4 of a pound when you are an adult. Your brain is unique because it's the most complex organ in your body. It takes the longest time to mature. It's the most complex, and I'll tell you that a little bit about that because we're going to talk about the lifespan of our brains. And it's the one organ that's literally changing on a millisecond basis. I am talking to you right now. You're creating new synapses, and I'll show you how you're doing that. Your liver does not do that. I'm sorry. Our organ is incredible, and we have what we call plasticity, which you've heard of nature versus nurture. Well, there's real science behind nature versus nurture. It turns out that your experiences, you take 2 twins, and the different experiences will actually literally build different levels of thickness in their brain based on if they become a piano player or a good golf player or they're really visual. It will actually change the way their brain is building synapses. And I'll explain that to you in a minute. And it's the one organ that's most affected by your personal history, the stresses that you've had early in life, the in utero environment, how much you exercise every day. And I'll talk to you a little bit about that. It's really an incredible organ, and it has so much ability for resilience, even as adults. And I'll show you how that actually plays out even in the aging brain. So this is brain. Remember I said it goes from 350 grams to like 1,400 or 1,500 grams. This is a scientific slide, but what I want to show you is if it goes, you can see it go across from the very tiny brain over there on the left to more adult brain. And what I'm trying to point out that my world as a doctor is I try to understand why certain times in development hit the brain with susceptibility to certain illnesses. And you can see up there what I mean. Premature cerebral palsy happens to premature babies. It doesn't happen to term babies. Seizures are really prevalent in early life. Autism only happens between 18 months, starts at between 18 months and 20, in 3 years. Why is that, right? So we can, what you see across those graphs that cross sideways is that we now know that the brain is going through these different stages. And the very part of the brain that's under construction at one point in time, since it does take 2.5 decades to 3 decades to complete, is the vulnerable place. And then, of course, when we get to the other end of life, things are going downhill, and then that becomes another vulnerable place. And that's why we see neurodegeneration, Alzheimer's, Parkinson's, diseases that are causing neurodegeneration late in life and not so much earlier. So neuroscience informs us a lot about our developmental stages. Infancy and childhood are an amazing time where there's going to be huge amounts of learning, where children can learn 2 and 3 languages flawlessly, and I'll explain why that happens. Adolescence, I'll show a couple of slides. I have a whole book on that. Just to show you like the perils and the opportunities that are that make up the adolescent brain, and a little bit about adult brain health, and a little bit about what we know about the aging brain that's looking very positive. So the first fact is the brain is the last organ in your body to mature. It takes until the mid to late 20s or longer, and there's a gender difference, and you can know where I'm going with that. And so let's talk about how the brain, so let's do a macro look at the brain, because I want you to actually come away with brain science. I think one of the problems actually in society right now is that neuroscience is such a new field because nobody could actually get inside the head, and we didn't even have scans. Think of MRI scans and CT scans. When I was in medical school, we didn't even have those things, right? So you kind of had to guess what was going on, and if the patient died, then you get to look at their brain. It's not an ideal situation. So this is, because now we have the ability to watch the brain and see how it grows, we have new data coming out of this field. And a lot of people who are sort of in their 40s and 50s and above, the word neuroscience didn't even exist when they were in college, basically, right? So we're talking, the public doesn't rightly have a lot of information about brain science. And, people can have a weak hand and think it's because they tighten their wristwatch too tightly, but actually they're having a stroke. And we don't have enough public service announcements and other things that would make us think about what does the brain do? Everybody knows what their heart does. They have a vague idea what their kidneys do. But they don't really understand what the brain. People think they love with their heart. It's your brain. There's a lot of, at least in females. So now, if we look at this brain over here, I'm going to just explain to you. So this is a brain. This is a beautiful, beautiful image from a brain. It's not a brain that I showed you that's a picture of a post-mortem brain. This is actually derived from advanced imaging, which has really, in the last 2 decades, been a huge game changer. We can create 3-dimensional reconstructions of brains. That's actually somebody's brain reconstructed just for my figure, from MRI scans, magnetic resonance imaging, you've heard of that, right? So, and what I'm showing you here, I've drawn hatches over it to tell you that if this person is looking, I can't see it, this way, I guess, I'm going the other way, the back of the brain is here and the front of the brain is there. And the cerebellum is where, motor systems and where you get your motor coordination. Occipital lobe is the vision that signals have to go all the way to the back of the brain to be heard and seen, from your eyes. Across the top here, you have the parietal lobe, which is for motor and sensory function. And we have a little map of our bodies with our leg here, our trunk here, and our head, our face here, and our hands arranged like this, literally as a little map. And the left side of your brain controls the right side of your body and vice versa. So that's how that works. And then the temporal lobe and the limbic system are deep in here. And these are parts of the brain that involve sexuality, emotionality. On the left side, languages in most right-handed people is here. And so this is a very risk-reward, addiction, things like that happen in this sort of middle system. And then the frontal lobe is really a very human place. We have the largest proportional frontal lobe of any species, and it's where we have our executive function, our judgment, insight, impulse control, empathy, organizational, cause and effect, right? That's what's up here, and the prefrontal cortex is even in front of that. So the brain actually, we have these areas, and they have to connect to one another, right? Remember I said we have brain cells, they've got to talk to each other, so they're sending messages back and forth and down the spinal cord, and that process of connecting one area of the brain up to another, that actually takes 3 decades to finish. And it starts in the back of your brain and moves forward because you need your elemental stuff like vision, movement, motor systems first. But the last part is your frontal lobe. So I'm going to do a little bit of a spoiler alert about the teenage brain. The teenage brain is halfway through this, so it's got the temporal lobe very, very well connected, but not, you got it, the frontal lobe. So they're on without the brakes of the frontal lobe to go, bad idea, don't do that. No, that's an effect of that. There's going to be, and so we sometimes call teenagers, Ferraris with weak brakes, so to speak. So that's kind of what's going on there. Now, when you look at this, beautiful, beautiful neuroscience has been able to show how, and some of this has been done here, actually. They looked at how the brain connects to itself across the lifespan. And what I'm showing, say, we'll just look at the bottom here, down this, at the bottom here, where we've made a translucent image of the brain. And you can actually, these tracks that I'm saying go from one area to another. We can color them. We can just pick a few. This is like a tiny fraction where we wanted to look and say, where is the cells that are in the top, where are they going down the spinal cord? Those blue, for instance. And you can see, you can track tracks, right? So what they did in the top, in A, was they took like how much these tracks are being used for the brain talking to itself, so to speak. And blue means very connected. So the brain was really connected up. But take a look at that lifespan there. At 4, 5, 6, 7, 8 years of age, the brain, the back of the brain is the back of the brain is on the bottom and the top is facing up. So the frontal lobe's at the top of this. And you can see it's not connected, right, until much later, until about age 20. So it takes a long time. The elemental parts, like the occipital lobe in the back or the parietal, the motor cortex, is connected. Children walk, they see, they talk, you know, but they don't necessarily think in an abstract fashion the way adults do. And so this is functional imaging. We call this functional MRI. Functional MRI means we can see, like if I move my left hand, I see the right part of my brain lighting up. And what they've done is just to see how many places are connected together. And this is just another picture, and I asked the gentleman to please play the little movie on this slide 11, just to show you that it was very beautiful what they've been able to do is reconstruct from these children that they followed through at different ages, how this brain sort of fills in over, but it's 20 years of development plus. It's not done. At the end of that slide, you can see there's still lots of little patches that are not finished. So what is going on inside the brain, and why is it connecting? This is important for you to know. This is now inside a brain. This is now brain cells themselves, okay? So here is a brain cell right up here. Let me see if this works. I guess it's not going to work, but that's a brain cell, and it has, it's sending a signal down to another brain cell, right, over on this side. So this brain cell is hearing through a little synapse, see the red arrow where it's coming and going all the way across the screen? It's sending a message. So when you have a thought, or you're doing a golf swing or a tennis swing, you're using your visual system, then you're using your motor system, and then your sensory system feeds back and said, I felt that, I felt myself hit that ball, and it's like there's a whizzing around your brain. You have like this set of connections, and if you keep practicing, you're using that same set of connections. It's kind of like a relay race, you know, going across your brain, and every thought has a very specific little map using some subset of those 100 trillion synapses, every little thought that we have. And when you do more of them, we can actually create stronger connections, and I'll explain that, and that's learning. So why is this such an issue for development? So here's one brain cell here, and it's going to talk to that other brain cell there, and it needs to go fast, just like it's an electrical signal. That has to zip down and talk to the next brain cell and cross that next synapse. Those connection points are called synapses, and I've got the synapse blown up there. And you can see that it has to go fast. But just like it's electrical, so just like the wires on the stage, they need to be insulated, right? Otherwise, electrical signals just dissipate if you don't have the wire insulated, correct? We don't have rubber in our brains, but we have a fatty substance called myelin, which is there, and it wraps and wraps and wraps around miles of these connections so that they're super fast. So they're, you know, you get split-second connections, right? That's how we can think so quickly, and things just go whizzing around our brain really fast at very fast speeds. That happens to be white in color. It's called myelin. Little tiny cells wrap the brain from the back to the front, get all the way to the front by the mid to late 20s. And that's the white matter. So that's myelin. And actually, just to put this in some context for you, have you heard of the disease multiple sclerosis? So multiple sclerosis is an autoimmune attack on that white matter. And so there, you can imagine if little cells were coming in and nipping away and making holes in that insulation, the nerve cell is fine. It's the insulation that's being attacked. And so what will happen is that's why people with multiple sclerosis can have, you know, waxing and waning symptoms, because it heals itself. And so once it's healed back, the signals can go fast again, right? So that's what, you know, multiple sclerosis is. So let's just imagine, though, in, say, a teenager, just to make my point, that This was a cell in the frontal lobe, and it's trying to talk to a cell in that reward system or peer pressure system, and the kid is like being goaded to go and shoplift or for some peer pressure thing, right? And the frontal lobe is trying to say, that's a bad idea, you could actually get arrested, probably not a good idea. Your brains would do that. Their brains, because it's not going fast, don't do that, and they act on their impulse, right? Much more readily, because they don't have the dampening from the frontal lobe because it's not myelinated yet. I've just shown you that. So that's one thing. So that process of myelination, and I told you we can map it. You don't need to worry about these graphs, but what you should do, this is the process of myelination. Look at this, from 0 to 30 age, look at the bottom. This is real neuroscience I'm showing you. I'm not watering this down. I want you to know it's easy to understand. Look at the x-axis, this for age, and it just keeps going up, right? And it actually continues into your 40s and 50s, that process of myelination. So it actually gets even better with age, okay? So there, kids and teenagers are not there yet, all right? So is everybody with me so far? So it's very cool. Our brains are the last thing to... You've already got this down, right? So now let's go back to more about how our brains work, because this is really important. So now we got the whole thing about how they're connecting fast, right? Down. Now what's happening at that synapse? This is the exciting part. The synapse is this place where one cell is talking to another, and it's in that blow-up bubble. So when I have a signal coming down from one cell, it triggers the discharge of little tiny messengers across the other side of the synapse to a receptor. And those can actually turn on the other brain cell or turn it off. So they come in two flavors, the on flavor of a synapse and the off flavor of a synapse. So we actually need the on flavors to learn. We need to activate our neurons when we're trying to memorize things. But for sedation, we use the off neurotransmitters. And actually, things like barbiturates, benzodiazepine, and even alcohol is mimicking our natural red neurotransmitter there called GABA. It's just a chemical mimic. That's how it works. So that's how almost every drug that affects your mental state works at one flavor of synapse or another, okay? That's important for you to know. So the reason why this is important is that those synapses actually are, the on versus off synapses are different at different ages. So if you look at this is work that we've been working on for a long time, is that it turns out that we have more synapses when we're young, and we prune them as we get older. You want to do that. You don't want too many synapses because they will actually cause things like epilepsy, some forms of mental illness are due to, autism is due to synapses in the wrong place that didn't go away. So we naturally want to prune the synapses, but there's a process of kind of a use it or lose it kind of, if you don't use it, it's going to go away. And that's all right, but if you want to keep it and keep it strong, you have to practice things. So the child brain and the teen brain have more synapses because they're in a learning mode. They're trying to build their brain for the rest of life. You can't build your brain with off synapses. You can only build them with on synapses, right? Last I checked. And so you can see that we have more excitatory synapses. And when I show this to some groups, these inhibitory synapses, I always say it takes a long time to become a boring old adult, as it slowly ramps up. But the magical thing about this is that this window is actually known to be a very special time, and it crosses from childhood into teenage years. It's called the critical period. And some of you may have heard about this. This is like what's captured in early intervention. This is why children can learn 2 and 3 languages. It's flawless. They've got all the machinery there. You had that many synapses, you'd be able to do it too, but you don't. They're gone by the time they get to our age. You've got some, but you don't have this. They just basically experience and almost learn effortlessly. This is called the critical period, okay? And adolescents are in this window too, so that's kind of a cool thing. We always thought it was just children, and now there's proof that it's also in adolescents. And there's gender differences in when we hit that peak, interestingly. So it turns out girls' brains, now I don't need to tell this audience, mature faster than boys. You didn't know that. And that's on average. Now, there are many early boys and many late girls, but in areas of the brain, I'm showing you real science, you can just appreciate these curves. The girls are hitting the peak of these synapses before they continue to prune them about 2 years earlier, if you look at that x-axis. And then you can go all over the brain and find different 2-year windows. It's about 2 years. And you can see like this really peak out sort of in 15-year-olds where, you know, the girls are organizing everything and the parties and they come home with their books, not without their books. And, you know, you know that you see that there's a big gender difference. And it's not just in the number of synapses. You don't really have to know this slide, but this is a very technical slide to look at how that white matter is developing, that process of myelination. And it turns out that the pink and just look at that middle bottom one, where it's going from 4 years to 20 years. And the point is that that signal is supposed to get less and less and less as you get older to show that you're really done. And look who's getting there first, the girls, right? The blue hits the bottom later than the pink, and then up top you can see it's you know, for this thing it's supposed to be going up, the girls get there first. So there's real science, and it's only been known, you know, in this last decade. And there are gender differences in brain connections, really minimal, but it's kind of cool that it's starting to be able to be seen. So we can look at those connectivity nodes, and boys and girls' brains are 99.999% the same, okay? But if you really want to tease out the few places they're different, our colleagues, Raquel and Ruben Gur, who are here at Penn in the psychiatry department, had published a paper in 2013 where they pulled out just the most minute differences. And it's very interesting that the boys' brains seem to have more within hemisphere back and forth connections, and the girls have more side to side. Now, I am not going to speculate on what this means. Nobody really knows yet, but it's going to be an exciting scientific, you know, discovery to understand what this really maps out as. So there are some differences, and girls are getting there a little earlier than boys. So I want to just tell you a little bit of the stages before we finish. I'll go through like a few slides showing a little bit more about infancy and childhood. I've just told you have this critical period in development. Let's look a little bit at adolescence. I'll talk briefly about the adult and the aging brain. So let's go back. How do we learn? Okay, so we're going to talk about you and me and all of us learning, because this is a very human characteristic, and it is modifiable, and it's part of this nature versus nurture effect, how you can mold your brain. We actually even call it plasticity, synaptic plasticity, because we can mold the brain. So what you're seeing here is a brain cell, kind of like the synapse that I showed you before over on the left, and if you activate it by a thought, or, you know, in the lab you can use an electrical stimulus, it will send a signal across to the other side. And that second signal will just sit there. But if you repeatedly, like as the practice effect, over and over and over and over and over, use that one circuit, like the tennis swing, repeating it over and over, getting that same relay race to be, you know, activated each time, kind of a magical thing happens. Calcium builds up in the cell and gets you to that middle point where it can actually turn on trafficking of more of the synapse to move up, these receptors, to move up into the synapse. And as you can see at the end, it can even change the gene expression to actually build a bigger synapse. So when you repeatedly use a synapse over and over again, you actually build a bigger, stronger, newer, faster synapse. That's memory. And look at the time course it's happening. Seconds, minutes, hours. That means anybody that's hearing something that they've never heard before from me is actually building real estate in your brain right now. And what's important is those, remember I told you it has to be those excitatory receptors, you have to have those. Those are the ones that are important. And you, after learning, it's a bigger synapse. Now, kind of nature's built more of the machinery for this, as I showed you, into the childhood and adolescent brain before it levels off to adulthood. So they have a strategic advantage. This is a learning time. They are learning machines compared to later in life. This is an opportunity for them. And so when we think about, are there age-related differences in learning, there are, and even at the synaptic level. So I'm going to show you a couple of slides so that you can interpret some real science. So where your real estate is being built right now is in a place called the hippocampus, which is a place that registers memory. And we can take, that's that in A. In B, we can take in animals a slice out of that hippocampus, keep it alive, and stimulate a cell that's a little gray cell that's talking to another cell, and record from the second cell. We'll see a little tiny blip on the oscilloscope. We buzz it, it blips. We buzz it, it blips. Now let's go down to the bottom here. If you repeatedly buzz it, it just is going to blip, blip. But if I repeatedly stimulate, like I was trying to tell you, that practice effect over and over and over again, suddenly that amazing things happens to the synapse and it grows. And if we were to continue to record from that cell, it would be a huge signal that you can see there further over on the graph after the repeated stimulus. Are you with me? So this is the science, and I've just superimposed the previous so you could see before and then after, right? You with me? So everybody can see that learning makes a bigger, faster synapse that you can actually record on an oscilloscope, okay? So we're gonna look at a couple of experiments with this graph where it'll be flat, and then you'll see a buzz, and then you'll see it come up, okay? And that's learning. So this is memory. This is memory. This is how things come to you so easily when it's memorized, right? Because you have an automatically faster synapse at that point. So what about the adolescent brain? So a little excerpt out of the book that I wrote in explaining this. The adolescent brain has much better, as do children, much better of this plasticity. And just by showing you these two, just take a look at the top right over there. There's an animal experiment first, and you're going along, and then you do that little arrow there above the number 20, and they buzzed it, and it comes up, and then it kind of comes down. It doesn't stay up as much. It's kind of like, always say, like it's an adult memory. You remember the first name, but not the last name. It's like fading as you speak, but you're trying. And then you look at the adolescent rat here, and you're going along, and you do that same buzz there, and look, it goes up higher, and then annoyingly, it even stays up and even gets higher. So they have a real advantage. It's the bar graph next to it shows you it's literally twice as much fast learning that they can do compared to an adult. So if you have an adolescent or a college student, because you're not done yet when you're in college, this is actually an important thing for them to know. This is sort of carpe diem. And in fact, there is a correlate to this, is that actually a new fact is that IQ can change during adolescence. And we never thought that. And we may know, it may be that we'll be able to see evidence of IQ changing all the way through the lifespan. We don't know yet. So this is an experiment done again, with beautiful, beautiful imaging, just to show you what neuroscience can do now. So we're looking at the top of a slice of a brain, and remember I said the left side of the brain is where language is. This is during a language task, and we can measure, with functional MRI, you can see little bright spots of where all the blood's flowing, that's that yellow, and the more it flows, the more you're using that part of the brain. And it turned out that this experiment was done they checked this at 10 years of age, and then they checked it again at 20 years of age, verbal IQ. And they found that a third of the people in IQ dropped their IQ between 10 and 20 years of age, a third of the people actually stay the same, and a third of the people actually raise their IQ. This is by 20 points. This is not trivial. This is a lot of IQ points going one way or the other. A 40 to 50 point swing right there. And this is between the ages of 10 and 20, when everybody thinks it's done by 6 or 7 years of age, right? And it's not. This is very cool, and for me, when I think about it, it explains a lot of things. Why, and we're very lucky in this country that we have an educational system that people aren't, tracked at 13 or 14, boys and girls. Oh, you're vocational, you're at university, because this can change. This is modifiable. And how do we know it's modifiable? This is another study to just show you that we can now we've taken it even further now, this kind of brain. We can make these beautiful 3D reconstructions of people's brains and actually measure thickness, and learning that in 2 years, you can see changes in thickness of the brain that you can measure, that even your head has not changed in size after the age of about 12. Your brain is actually filling up the space in there. It's still growing. The cortex is, and the more it grows, the thicker it gets, the higher the IQ in this test, and the less it grows, the lower the IQ change in that window. So we're learning a lot about that. And so now, there's been studies now to look at children between, this was a study looking at 2 time points, 14 to 17 years of age, and looking at what happened to IQ in that window. And they turned out that if you look at this top graph, the more they were reading at time 1, predicted a higher IQ at time 2. So, my advice when I give this talk to high schoolers is you read and you write. This is modifiable potentially, and we have to do a better job of figuring out what needs to be modified. But again, this would speak to, there's amazing capacity that was completely under-recognized, I think, in these high school and college years. So, learning and aging. So I've just given you a little bit of that. Learning is the best in the younger brain. I just showed you that. But adolescence is a time where learning mechanisms can really be challenged, because they're very good at learning good things, but they're also, unfortunately, really good at learning bad things. So the problem is that adolescents put themselves in harm's way, as part of their novelty-seeking behavior, and so they can actually be damaging their brains, which are like sponges, and they can be exposing themselves repeatedly to bad things as much as good things. One quick thing I'll just show you is, those of you that have been around young people, they're amazing multitaskers, incredible. They're doing their cell phones under the table and having full text conversations while they appear to be looking at you at the dinner table, and they're not. And they are incredible multitaskers. They have learned to multitask. But one really cool thing to tell you is that old school, I think, still wins. This is a study done on University of Missouri undergraduates, and they're trying to teach them, it's a learning curve on the top, and it's done with full attention versus distracted at retrieval or distracted at encoding. And you can see the learning curve is really good and high on that top band, but when you distract somebody when they're encoding, which means when they're putting a memory down, like when they're trying to memorize something, it's really bad. Look how much lower this is. And then, of course, when they're trying to bring it back, if it's distracted. So we do know that while our brains have this capacity, they still can learn most efficiently once you hit late adolescence and adulthood when you just focus, right? So that's really important for us all to know. What I was talking about with the adolescents, though, is that they have this ability, they've got, just like children, they're able to learn and create faster synapses. When you repeatedly stimulate, like with a thought, a vocabulary test, you would get a stronger synapse and you'd have memorized, right? Well, that's repeatedly stimulating, say, in the hippocampus. Unfortunately, there are other forms of repeated stimulation of other things, and you see addiction is simply the same thing. It goes from a simple synapse to a big fat synapse. It turns out addiction is a very human quality. We all can become addicted, and it is simply just a form of learning. It's all it is. It's just in another area of the brain that is in the dopamine part of the brain. It's using dopamine in the reward system. And the repeated exposure, the brain adapts, and then it builds a stronger receiving synapse, and it's the I want it, I want it, I want it synapse. That's addiction. So addiction is an absolutely human quality, and it can happen to anyone. To anyone. Any of our brains could become addicted. And this is important because it turns out teenagers can become addicted faster than adults because they're just better at plasticity, right? This is a better form of, this is plasticity just like, the good news is that if you get it early, you can reverse it because they're still malleable. But if you go into your 30s, having been addicted as a teenager, it's stuck there. And one example of this that we can bring up is addiction in adolescence. From the animal data we show, here's an animal, old animal versus an adolescent, take nicotine, which is legal. And this is looking at like how much does these things, how much does nicotine turn on the brain? This is an animal that's sitting in a cage. It normally gets plain water. You give it saline, and this top, this is just showing the bright is the on parts, the brain, part of the brain that's turning on. You can see here the adult rat doesn't even know, doesn't even care that he's just had saline. His water just got switched. The young animal is up and very alert, and it notices even just that the water got switched to saline. But then you put in nicotine, and it does get the adult to rise. But look at how many more fold the immature brain responds to an addicting substance. It's just huge. And so one of the interesting things that we've been working with the Surgeon General, actually I was on a report from then, is that the people aren't smoking cigarettes so much anymore. That's not the problem. It's vape. Vape, 25% plus of kids and college kids are smoking using vape cigarettes. And it can be 3 to 4 times as much. This was something I pulled off the internet. They're bragging they can get 36 milligrams into one single vape. This is like mainlining this into the adolescent and young adult brain. And indeed, just this month, Journal of Pediatrics has shown that, yep, just as we expected, exposure to vape cigarette in late teen years makes you become addicted to nicotine much faster than an adult. So this is important to know. And why is that? It's not just the synapses. It actually turns out that the part of our brain, remember I said that it's like here, that's the reward circuit, it's just on more in these kids. They can get addicted faster because their brains turn on more in an addicting situation. So here's a part of the brain called the nucleus accumbens, and this was a game that was played. The brain is being sliced this way. People are being challenged with a kind of an addicting risk-reward task. And they looked at kids from 5, I guess it was till 10 to 25, and they measured how much this nucleus accumbens deep in here, that's actually connected in your teen years, by the way, before your frontal lobe, is lights up when you're in an addicting situation. And look at the difference. It's like twice as much compared to adults. It's a peak right in this window. They're on, their brains are very highly connected, and this is an area that is really driving the younger adult and teenage brain. And we have the science to show it now. This is the first generation of teenagers that we ever even considered was a brain stage, right? We didn't even think it was. So the teen brain, I'll stop on the teen brain, but the teen brain is really, this is how you can apply neuroscience, right? It has heightened synaptic plasticity, which now you know what synaptic plasticity is, right? You know some neuroscience. It's got a heightened reward system, I just showed you that. So it's like a double, it's a double hit for drugs and stress and all these things that can affect synapses. So they're very, very vulnerable. This is a myth that we need to break the myth that, oh, teenagers are so, resilient. They aren't as resilient. They're actually more vulnerable under some circumstances. So just in talking quickly about, so we now know, how things like that, we can apply science to these socially important questions, like what on earth is going on with the brain when these things happen to it. So I'll just show you a couple more things. That this is now going outside of the teen brain, but relevant because teenagers all think they are, stressed, and they are, is that stress has a terrible effect on learning, on all of us. I'm sure you've all been in stressful situations, and you really are impaired. And what's happening here is you take a look at the little thing with the cat. The green is the score that this little animal gets when it's sitting in its home cage. Red bar there is when it's been moved someplace else. It's in a little bit of a strange environment. Doesn't get as good a score. You put a cat outside and it's not even on. And when I give this talk to teenagers and I show this and they're like, oh. So, but where is that happening? That's cortisol going up in our bodies. And if we record from the brain slices, you can see down there, you have the bottom one. It's much lower response. But it's happening in the middle. It's sort of cutting, it's preventing the learning from consolidating, okay? It's preventing learning from consolidating. And so you kind of think you're learning, but you're not, and you're really stressed out. So this is important. It's a really biological effect. And so what about our children and adolescents, and is there an age dependency to stress? Well, across the lifespan, actually, it's the adolescents that respond to stress more than anybody else. So here's an MRI study that was done looking at the part of the brain, the fear part of the brain. That's what just blushing red there in the brain. See, now you're knowing the amygdala. And this is they showed people videos of concerning faces, of just really frightening kind of concerning faces. And they watched the amygdala and saw how much activity, how bright was it, and that's mapped there. And you can see, once again, that grayed out zone, it's the adolescents that are responding to stress more than even adults. So we all respond to stress, but it's age specific, this big effect. And so sometimes when I'm talking to people, I say, give your adolescents in your world a little bit of a break, because they are experiencing emotion in technicolor to your black and white. And you have to be a little bit understanding and apply the science instead. So the other thing that we're noticing that's very age specific, because of the parts of your brain that are actually coming online, is the emergence and peak of mental disorders that come and go in a very, very specific lifespan. So it turns out that you actually need, remember I said your frontal lobe is not fully connected, it's connecting through your 20s. You need your frontal lobe connected, sadly, to sort of do mental illness. So to have the full manifestations of schizophrenia, bipolar, or depression, you have to have your frontal lobes actually somewhat connected. This is why we see what appears to be an epidemic of the onset of major mental illnesses in this window. It's not that the college campuses are brutal. It's not that there can be triggers in the environment. It's not the environment as it's the inside of the person that is really driving this peak. And one of the things I've been doing with the health, HHS, Health and Human Services, is 1 in 4 people have mental illness, right, in our society. And anxiety is huge in this window. And it comes on in this window. 60–80% of people that have a major mental illness, like a schizophrenia or depression, it's come on between the ages of 16 and 26. It is epidemic in this window. And yet we don't screen for it. We get colonoscopies at 50 because of some very small chance of colon cancer, breast mammograms constantly, PSAs for men's prostate. There's nothing like the incidence and prevalence of this specific window, which is enriched for the onset of mental illness, and we don't screen for it. It's insane that we don't screen for it more. You can do very detailed psychological testing, not just a survey that's given by the pediatrician. Do you feel like killing yourself? Have you, I mean, it's like that it is so basic, it's really sort of embarrassing. We need to do a better job. And I think science will give us some biomarkers of this very soon. It's coming in the next decade. So, and of course, we think about our lives and our teenagers' lives, and I'm pointing out teenagers, this has all of us, the effect of social media on stressing you out and pushing you kind of to the edge, it's a real concern. So where are teens in development? I've just shown you where adults have like fewer synapses, they've got a lot, children and teens, and then we go down as we go through adulthood. And then what about white matter, that connectivity? We actually grow that through into our 40s and 50s, which is very cool, because adults are kind of lean and mean. We don't have a lot, but we move fast with it. So now, if I want to just the last two things quickly talk to you about, we've talked about stress, we've talked about kinds of why the adolescent period is really special, as is the childhood. What else can we do as adults to make our brains work better? And so it turns out even adults' brains can change. So it turns out, here's a study, you don't really have to know the science, but this study was able to look at parts of the brain that changed in an adult, in a 50-something-year-old set of adults. And the little yellow spots are areas really important for learning and memory that actually this hippocampus, remember the hippocampus? That they actually gain size and function after they've learned. So it is happening, and we are doing it. You are doing it at this moment. And there is hope for us as adults. We can do it. We probably just need to bang our, repeat everything 100 times more than an adolescent, but we can do it. And so there's now beautiful science that's now showing that. And there's really cool things about aging brains. You can push the aging brain to act like a young brain by a lot of enriched environment. And so it turns out you really have to push it a little harder. But here is a study looking at young versus aged. And see that red bar is low in the aged. But when you've trained the aging animal, you get a higher, it looks more like the young. So if you really push it and the cells come back, you grow, you get new cells, and you prevent the age-related loss if you stay mentally active. And another part is exercise has been shown to promote brain cell growth and birth. And it turns out, quite interesting studies are looking, we can actually measure these cells that are coming on, that it turns out that sedentary brains don't do very well. That's the yellow bar. The green is if you've exercised just a high-intensity interval training. That doesn't do it. It seems to be the running, in animals it's a running wheel, but sort of this long, prolonged, consistent exercise that seems to be the best at bringing our brain cells to come back in this special area of our brain. So, And so one of the things that I just want to point out to you is we actually know a lot about degeneration and Alzheimer's and how it's blocking this learning process. You've heard of plaques and tangles and A-beta and all this stuff whenever you go to an Alzheimer's lecture. Well, it turns out that very molecule acts to just block the synapses. It's stopping the synapses. And so when you can do experiments, you can see that red bar, they're not learning as well. So we're actually even beginning to understand why learning isn't so good in brains of people that are demented. And that we can actually, modify that, though. Studies are showing that enrichment training can actually counteract all these things that we know that happen badly in AD, which is Alzheimer's disease. So there is hope. There's a lot that's modifiable. Research is showing a path to this, to our brain health. So brain stage matters. Learning can happen at any age. Biology dictates that we that we require more support and effort as we get older, and there are tons of opportunities and strengths in the younger brain, but also, as I hope I've shown you, is a double-edged sword that we need to be mindful of. And learning in the aging brain is modifiable, so stay tuned for the new neuroscience. So just to close with this synaptic learning, it's very, very high in infancy. It's great in childhood. Teenage is good. Adult is great. And we kind of have to talk about this, but the connectivity, that myelination is going up. That's what kind of saves us, as we get older, and the frontal lobes are key here. So I will end there, and thank you for your attention.